Hi guys. So I wanted to go over the solutions to a quiz that I gave the other day on a low pass filter circuit. So you can see up here we've got a passive first order low pass filter. So we're feeding 50 volts AC into this, and you can see that we're taking V out across this capacitor right there. So the question is, if V out is 12.5 volts, how much has V in been attenuated by? So remember, we're feeding in 50 volts AC, and at V out, we're seeing 12.5 volts AC. So I want to know how much has Vn been attenuated by in this case? Well, we know that there is a formula that we use to determine signal attenuation, and that is 20 log 10, log base 10, V out over V in, otherwise known as gain, by the way. Uh, and that is gain in dB. In this case, there's not going to be any gain because we don't have any amplification happening here. So it's just going to be attenuation, which means we're squishing the original signal down. So we know V out, it's 12.5 volts. We know V in, that is 50 volts. So we just plug it into this equation. 20 log base 10, 12.5 volts over 50 volts. And let's see what we get here. So 20 log 12.5 over 50. I am getting minus 12.04 dB. So the original signal in this case has been attenuated by minus 12.04 dB. And if we look at the Bode plot of this filter, it looks like this. So along this axis right here, this is frequency. This spot right here is the critical frequency of this filter. That is where it starts cutting things off. In this case, this is a low pass filter, so you can see that when you hit this frequency right here, it's going to start rolling off high frequencies. So the critical frequency is going to be 1 over 2 pi RC in this case. And we know the slope of this line as well. It is minus 20 dB per decade. Or minus 6 dB per octave. So that's the slope of this line right here for a first order filter. So you can see that if we change the frequency of this input signal right here, so we move up like this, eventually we will hit the cutoff frequency right there, and our filter will start rolling off frequencies. So you can see that in this case, the higher the frequency of V in, the more attenuated it becomes. So let's do another question. So this one here, we don't know what V out is. We just know what the attenuation is at V out. So we know that at the output, we see that Vn has been attenuated by minus 23 dB. So we know that the attenuation at the critical frequency is minus 3 dB. And I'm asking about this spot right here, which is minus 23 dB. So the signal has been attenuated by a lot. Okay, so the question is, what is the voltage across the capacitor when we're right here? Well, let's see. So we're going to use this equation again, 20 log base 10 V out over Vn. Okay, so in this case, we know the attenuation in dB. It's going to be minus 23 dB, right? That's the spot that I'm asking about right there. We know Vn as well. It is 50 volts. The only thing that we do not know in this equation is V out. But that's simple enough to get to. So let's do a little bit of algebra. So the first thing I'm going to do is I'm going to divide both sides by 20. So minus 23 dB over 20 there. And then on the left side of the equation, we've basically got log base 10 V out over Vn. Okay. So let me figure out what that is. Okay. Did I get that right? Yes. Minus 1.15. Okay, so I'm going to rewrite this so it doesn't look so messy. So it's log base 10 V out over Vn, which is 50, equals minus 1.15. Okay, so let's see here. How do we undo a log base 10? Well, it's just 10 to the power of all this, 10 to the power of all this. So it's going to be 10. And let me check my sign here. I'll do that in just a second. I'm just going to put this up here right now. Okay. And then over here, we've got V out over Vn. All right. So let's bring Vn over here. So it's going to be V out is equal to Vn times 10 to the power of 1.15. And here's where I'm going to check my sign. So if the signal Vn, the 50 volts, has been attenuated by minus 23 dB, that puts us right there. Then what is V out? So if we were making Vn bigger, we would keep this exponent right here positive. But we actually know that we're making Vn smaller. See? This is Vn right here. And then as we increase the frequency, we make it smaller. And so there is going to be a minus sign right here. So let's see what V out is going to be. So we have 50 volts, that's Vn, times 10 to the minus 1.15. And it looks like V out is going to be 3.54 volts. So when Vn, the 50 volts right there, has been attenuated by minus 23 dB, then we would be measuring 3.54 volts at V out there. All right, so that's all I've got for today. Next time, we're going to talk about high pass and band pass filters.